So then the idea of a reduction is if one algorithm has, so what this is, non-deterministic polynomial time. What's a reduction? If one problem has a fast algorithm, then all problems have a fast algorithm. And we're not going to go do this whole, I have a whole long reduction here that we could do if we wanted to. But given our limited time, I'm going to say let's not focus on it. But you do reductions in 2001, you do reductions, and you're supposed to know how to do reductions. So we're just, when we're switching topics, we're changing our notation. So before we had a circuit C and an assignment I, and now we have the input is I and S is the solution. It's just because we're moving into a different sort of world here. So here's the, let's just make sure we can state the clause sat problem in first order logic. All right. So what is the input to clause sat is a bunch of clauses, right? And what is a clause? There's a clause, right? What's it's the our input's the and of a bunch of clauses, and you want to satisfy all of these clauses, right? And what is a clause? A clause is the or of a bunch of literals. So it's B or C, not C, or not E. And what is a literal? It's either a variable or it's negation, right? Does that make sense? So you don't think this comes up in computer science all the time, right? I have a bunch of things that I want to satisfy. And how do I satisfy them all, right? And I need to, I had to find, is there a way that I can satisfy all of these clauses, right? So you can imagine that this is, suppose I'm building a robot and I want to get the robot to stand up and walk out the room, right? So I have to say, is there a way for my robot to act so that what? So that I do manage to stand up and I do manage to walk and I do manage to get out the door, right? And I do manage to not kill anybody, right?
Last one's always the hard part.
Yeah, all these hard parts, right? All these little tweaks. I just finished season 2 of Westworld, so I'm all up on robots killing people. All right, so here, what is the solution to this? A solution is setting each variable to be true or false, right? And when is the solution, when does it satisfy, right? This solution satisfies this input, this set of clauses. Well, here, this A is satisfied, right? A is set to true. So here's an A. So that satisfies this whole clause, right? Now that clause is satisfied. And this clause is satisfied, right? Because C is set to false, and so not C is true, right? And that satisfies that clause. And this clause is satisfied because B is true. And this clause is satisfied because D is false. And this one's satisfied because C is false, right? Everybody kind of buy what satisfied means, right? And so what are we asking for? Right, that says that S satisfies the whole thing because it satisfies each clause. And this input is a yes instance, i.e. this thing here is satisfiable if what? If there exists a solution that satisfies it, right? And what does satisfy mean? Well, it means there exists a solution such that for every clause, the clause is satisfied, right? And what does satisfied mean? Satisfied means for this clause, there exists one of the literals in the clause that satisfies the clause, right? There exists a variable here, B. Variable B satisfies that clause, right? And what does that mean? That means either the variable is unnegated and is in the clause, right? It's here, it's unnegated in the clause, and I set it to be true. Here, I don't know why there's a false there, right? Or that's clearly a typo there. Or it's negated in the clause and you set it to false, right? Does that make sense? Right? So there is a perfectly good first order logic sentence, right? Everybody get this first order logic sentence? Asking whether this, if for this input here, I is a free variable, and if this is true, then this thing is satisfiable, right? So now I could ask you another question, right? Here's a bunch
Sorry,
of,
Jeff, if I could interrupt.
yeah,
Can you, if I can find a model that satisfies the, oh, I'm sorry. I'm sorry, I lost my train of thought, so I interrupted you for no reason. I
no,
apologize.
no, it's all good. How would you prove this, right? You would prove it by, yes, coming up with a model. And what's coming up with a model? Coming up with a model is, the key is finding this S, right? If I could tell you S, then the rest is easy, right? Because there's only a few clauses and I could check them all. The hard part is coming up with this S, because they're an exponential number of S's, right? So you're absolutely right, Conrad. The hard part is coming up with a model that satisfies well, actually, no, I mean, it's, yeah, I mean, in this way, yeah, I mean, I guess usually we come up with models which prove something is false, right? But here, we just have to come up to show something to prove it. What does a proof look like? A proof looks like I have to come up with the S, right? And that's hard, coming up with the S.
So while that S is not a proof, it is kind of it does lead us to a proof.
Yeah, yeah, right. The S is close enough to. The point is, yeah, the point is that if the fairy godmother gave me the S, I could finish the proof, right?
So Professor, what is X here?
Oh, X is one of these variables, all right? And X is any variable, right? And here's a clause, right? Why we came up with some, oh yeah, here, why does this solution satisfy all these clauses, right? Well, why does it satisfy this clause? It satisfies this clause because there's a variable X, which in this case is C, that is negated in this clause, and we set the clause and we set the variable to false, right? How do you know, if you gave me a solution and my right, if I came up with a solution, right, I wanted to do a proof, I come up with a solution, then my adversary names a clause, right? The adversary names this clause. And then I have to prove that this clause is satisfied. How do I prove that this is satisfied? I name one of its literals. I name one of the variables in it. I show that the variable is negated in this clause, and I show that I set that variable to false, right? That proves that this clause is satisfiable, right? Right? Did that answer your question?
Yes.
Right? So here's another problem, right? I have a box. I give you a box like this, and the box has two columns with circles and X's in this one column. And I give you these cards, and the cards have holes poked out in them, right? That's my input I, is these cards. And what are you asking? Well, the goal is to take each card, let's see here, and we flip some of them, all right? Here, A, you see I didn't flip A. But C, how did I get card C? I flipped it over, right? So in the front of the card is written C, and on the back of the card is written not C, right? And so what I do is I take my card C is if I want, I can flip it over so it's upside down, right? Everybody buy that? And so that's a solution, is I choose which cards to flip upside down. And what do I do with them? I stack them onto the box. And you'll see that when I bring a card in, if there's a hole, I can still see through, right? And if there's not a hole, here there's not a hole. So I put the card on top and it covers that X, right? So I want to know, is there a solution that covers all of my X's? Right? Right? Everybody get the problem? So we can say, hey, given what is I is a bunch of cards. And we say it's a yes instance if I can cover all the X's. And what does that mean? It means that there exists a way of flipping the cards that covers all the X's. And what does that mean? Oh, here's a solution, right? It says flip some, it says don't flip others, right? And then, well, what does it mean to flip all the cards? Sorry, what does it mean to cover all the X's? It means for every row, I cover the X in that row, right? And what does it mean for a particular card, right? Right. So how do I know that I cover a particular X? Is there exists some card that covers it? Right. Right. So there exists a solution, i.e., a way of covering all a way of flipping the cards, such that for every row, there exists a card that covers everybody, who covers that X. And what does it mean to cover an X? A card covers an X is if it doesn't have a hole over here and I don't flip it, right? Or it doesn't have a hole on the other side and I do flip it, right? Does that make sense? So here we have two first order logic sentences, right? And it's hard for me to prove either of them, right? Why is it hard for me to prove it? Well, it's hard for me to come up. The hard part is knowing how to flip the cards, right? But remember in our oracle game, we said if we have an oracle, we can solve the game. We can prove what we want when we had an oracle, right? So what I'm claiming is if we had an oracle for that first satisfiable problem, we would have an oracle to solve this problem. And if we had an oracle to solve this problem, we would have an oracle to solve the other one, right? And right here we show that if you could solve one, you can solve the other. And if you could solve the other, you could solve one. And we're not going to do the reduction, but here's just ways of showing that if you could solve one, you could solve the other, right? In the bottom line, what it works down to is if I have an oracle that could solve the card problem, right? What do I do with that oracle? I give the oracle a bunch of cards, and the oracle gives me a solution, right? You guys think that my game in oracles is absurd, but it's playing out in the way we do computer science, right? If here's an algorithm that you give it, if you give it the cards, then the algorithm gives you the solution, right? And what do we do with that? We build from it, we build a machine that you give me a bunch of clauses and I will tell you whether it's satisfiable or not, right? And how does the algorithm work? You give me a bunch of clauses, I translate those I translate those clauses into a bunch of cards. The oracle tells me whether there's a solution to the card problem, and I give the same answer, right? I take his solution, I take the oracle, her solution, and I translate it into a solution to this problem. Right? You following that? So that's the whole idea of an NP reduction. Are people sort of getting that? Any questions about it? Conrad's got it. And then of course you have to go in the other direction. You have to say, if I could solve the SAT problem, then I could solve the card problem. There are more and more, lots of slides on that, lots of slides on that. All right.